efficiency for electronic devices for defense industry applications. My name is Optpelectronic. I'm an assistant professor at the Harvard University. In my presentation, I will focus on two main points of my research journey. First, I would like to talk about my innovative photographic design, and that was the main part of my PhD study at Middle State University. Then I will discuss my recent postdoctoral research on advanced infrared semiconductor lasers, which are carried out at Ohio State University and Baylor University in the United States. As we all know, infrared photodetector devices play a crucial role in various defense industry, from night vision system to advanced laser vision designs. This kind of technology greatly enhances the performance of modern defense systems. This is my academic journey. I graduated from Optpelectronic University Physics Department as a high honor student. I got a major from Mathematics Department, and I received my PhD degree in micro and nanotechnology at Middle State University. My PhD thesis title is Biological Engineering for High Performance NBM Photodetectors. My thesis was selected as the best thesis award, best doctoral thesis by the institute. During my PhD, I also worked on a typical project. This project was based on my doctoral studies. And during my doctorate also, I worked on a commercial infrared detector project was funded by SSM. After graduation, I started as a postdoc researcher at Ohio State University. It was funded by CBEC. CBEC is a kind of artist company that it was funding a basic project. After this project completed, I started also as a postdoc researcher in Baylor University on antimonite-based mid-infrared laser project. This project also funded by NSF in research. First, I would like to mention about my doctoral study. Most optoplectronic devices are based on CAN drive structure. But this kind of structure, when you decrease the bandwidth of device, it means if you want to see infrared region, this kind of dark coding mechanisms, it means the noise can be very increased. For example, GR currents, it means generation recombination current, flat as tunnel current, band-to-band tunnel current, and surface current. And then that structure is developed a kind of alternative to CAN junction diode. Since there is no any depletion region, this is depletion region, and then structure there is no depletion region, and since because of that we are flat as tunnel and band-to-band tunnel, and also surface leakage current can be suppressed without affecting. For example, if you want to buy an infrared detector in the market, mostly you will buy as a material cadmium telluride or indium gallium arsenide. This material system I will mention the type 1 material system because of the band alignment. You could apply this structure directly. Now I will explain more clearly. Okay. If you yes, the balance band discontinuity is sorry, maybe this information can be very far from your background, but I will try to explain more basic way. This in semiconductor there are two carriers, charge carriers. We say one of them is electrons, one of them is holes. Holes can flow also, sorry, electrons should flow and also holes can flow, but because of this band alignment, type 1 structure, type 1 band alignment couldn't be applicable for this NVN structure. Only antimonide-based semiconductor type 2 or type 1 are the most suitable material systems to obtain NVN better architecture. However, type 1 material systems such as indium gallium arsenide and mercury cadmium telluride, which are the most commercialized detector material systems, are not applicable for NVN structure. Here I try to show what I did in my thesis. For example, this is a high bandgap material, indium gallium arsenide. Bandgap like that. Bandgap change the color of, for example, LED. If you want to see, if you want to emit infrared, you need to use low bandgap material. For example, indium gallium arsenide, not exactly low, but the 1.55 micrometer. Or if you want to see a higher bandgap, for example, if you want to emit UV, you need to use nitride-based material. Nitride-based material, high bandgap material. This because of that. For example, I would like to show first NVN structure. You see, ideally you need to use barrier. There is no key layer. This structure is very simple for fabrication. But if you want to use this kind of material system, your structure looks like this. Because of this balance discontinuity, holes cannot flow, and your structure will not work, and your detector will not close. But if you, for example, if you grade the value when you unlock indium gallium arsenide system is dynamic graded from indium gallium arsenide to indium gallium arsenide, naturally a quasi-electric field emerges. Because of the quasi-electric field, this balance band emerges. If you place N-type and P-type delta topic layers are inserted properly both sides of these layers, you can cancel this electric field. And it means you can cancel this valence band. And this structure normally you can apply the type 1 material systems. Now you can apply using these techniques. This is my simulation. You can see the delta doping layers, these layers, delta layers. Delta is very thin semiconductor layers. And if you insert both sides of these graded layers, you can cancel this balance band. And you can see in my simulation, when I increase the doping concentration of delta layers, the balance band discontinuity is getting small. And you can see the most optimized concentrations is this, and you can see the balance band almost disappear, And our bank of converted bank varies high enough to measure this, we need optimum and then performance. If you want to increase the doping trails, the electric field also increase the dark current, and because of this simulation, you can find an optimum concentration. This is our paper. Actually, this is my thesis. We published this paper after my graduation. Actually, we applied a third project. Because of COVID-19, we finished this project after my graduation. We can see my design can be applicable on conventional detector structure. This is our sense. You can produce a camera using this structure. It doesn't matter. It depends on the project funding amount. But because of this structure, you can use a dual band because there is no p-type, and you can, for example, if you apply here positive, if you apply here negative, you can get this side electrons. If you apply here positive, you can get electrons from this side. It means this structure can be worked as a dual band structure. And this graph shows us I mentioned to you there are some darker mechanisms. It shows that this dark mechanisms perfectly suppressed, and this graph also shows this dark current of this device are very low.
So why wavelength is 2 micrometers?
Okay.
There are some of 3, 5, 8, 12, for example. It was more efficient.
Oh, okay, perfect. This question is very nice. Normally, okay, I said to yes, indium gallium arsenide is the natural band cap or cutoff is 50-50, so 55 micrometer. But here we try to balance this wavelength, and because of what? Because of if you want to increase the wavelength, you can see the band of the cloud. Because of that, actually this is the beginning of our study. We can exceed this wavelength. We say this wavelength after 1.55, we say extended silver, short-wave infrared. If you want to see beyond the cloud or dust, you need to increase the wavelength. But band cap of this in gas, in gallium arsenide, naturally here, cut off here. But because of the, if you want to balance this wavelength, you need to change the mole fraction of this material, and because of that, we say extended silver. And this is our aim, this CD extended silver. And it is very important for seeing beyond the clouds.
Is there any limitation distance?
Oh, yes, perfect. There are limitation depends on what? Depends on the crystal dislocations, crystal defects. And if you want to, you can, for example, if you decrease the gallium, you can go beyond. But this, you see, indium phosphide is kind of, you say substrate. It's a kind of, think about a kind of building. You need to use the same the distance between these columns, and if you decrease or increase this mole fraction, the columns getting distance getting smaller, and crystal structure getting worse, and the efficiency of detector will be very. And because of that, we try to ideally, you need to use this mole fraction for the lattice match. But if you want to see band, you need to decrease the value mole fraction. But there is no very there is no limitless adjustment because of this crystal lattice constant. There is some kind of margin. For example, you can use indium arsenide, but your detector maybe cannot go because of this location crystal defects. And this is for we can go further. How much? Maybe 2.7, but 3. I don't know. Maybe it will not work.
What is the in this square?
This or
No, the left one.
yeah, okay. Actually, these are complicated devices. This is
You show the size.
size. Size.
It shows the detector size.
Actually, this only the detector size that much. You see, this 20 micrometer. Our detector size is also limited by wavelength. You couldn't go very beyond. For example, you couldn't produce 0.1 micrometer infrared detector because of the wavelength. Wavelength limit the detector size. These are all detectors. This complicated device. And this dark curve, you can see also it works as a kind of blue band.
You can use this as a detector, right?
Yes.
So how do you measure its efficiency?
Yes, there's quantum efficiency measurements setups. We were using some spectrometers for that. Now I couldn't remember, but FTIM, we are using FTIM.
All right. So did you compare your?
Yes, there are black body radiation. We have also reference detector.
Okay.
We compare with the reference detector. We have a commercial detector. We try to compare it.
Does it affect the crystallization, affect the reflection of the gas?
Reflection.
Does the gases, how can I say, crystallization affect the?
You mean the measure crystallization?
Yes.
Yeah, yes, of course, because we need to use pure material, and because of that, we use this system. This system we say MD. MD means molecular beam epitaxy. It is very high. You need to decrease the vacuum. You need to decrease the pressure, and you need to go very high vacuum. For example, this holes, this tubes, you will apply liquid nitrogen around this system, and also we are always vacuuming, and it shouldn't be any very atoms. You need to very precise in terms of this vacuum, and because of that, you need to use this kind of equipment for crystal growth. Yeah, crystal and this we have in this technical university we have two MBA systems for different materials. For example, if you have one system, you cannot grow every crystal. And this, for example, is for mercury cadmium telluride material growth. And yes, thank you for your answer.
Such a defect if you use, does it require a cooling method?
Yes. For this wavelength, you don't need to cool. But if you want to see, for example, 3.5 micrometer wavelength, you need to cool down the detector. And for example, here we, actually in my during my doctorate, I also involved some project. In this project, we grow this kind of wavelength material. And if you want to see very low, very long, I mean, we say mid-wave or long wave, you need to cool down the system. Because of this structure, you okay. If you want to see long wavelength, you need to decrease the temperature of the device. Because of what? Because of this dark room materials. This system, this structure, automatically you cancel the GR as some bad tunnel. It means the cooling requirement is getting decreased. Cooling requirement is very critical things for the GR. For example, if you want to put a drone, the system produces also noise. If you use low noise, if you want a low noise detector, you need to use this kind of structure for low cooling requirements.
So then the operation time will be limited. For example,
Yes.
for NCT detector, because I remember if you have a 50 bar, for example, ratio of cooling, and it was limited to 3 minutes, for example.
Actually, detectors has some cooling systems. You can use thermoelectric cooler, but for if you want to see very long wavelength, thermoelectric cooler will not work because you need to decrease, for example, minus 100 Kelvin or, for example, around sorry, not sorry, Celsius. Excuse me. Minus or for example 70 Kelvin or 100 Kelvin, you need to use cryo cooler. Yes, cryo cooler can be produced very also this size, and this device also produces some noises. But I believe that the working time not just for example 10 minutes or half hour, more than it should be very long time for you because your drones or your aircraft require very long time. And this and because of this structure, we can say we can produce high operation temperature detector. And now maybe next my plan apply for different material application this structure for different, for example, mercury cadmium telluride or other material systems. But this paper show my design works very well, and I can apply this design different material systems. Okay. This is my actually after my graduation, after COVID-19, not exactly my graduation, I started working as a postdoc researcher in Ohio State University. Actually, this project is called the Dark Laser project. Was founded Seagate.
Before continuing with this, did you compare your proposed detector in terms of sensitivity and resolution, etc., to conventional ones?
In this study, not yet, not yet. But because of some problems, COVID-19 and my graduation, actually we finished this project when I was in Ohio, and I couldn't continue further. But my plan, I hope I will apply a project for the producing camera, and I am planning to this kind of this measurement. It's very basic.
All right. You have shown us that you have won the best thesis award, right?
My thesis award, yes, not this.
It was for some
Not
good, great achievement, right? What was it?
actually, my great achievement is my proposed. I believe that the institute, I don't know much, but the institute, I believe that my first I did design, and first I produce a simulation, then we earn a project. I think because of that, they get. I don't know why exactly. Actually, this is my department. Also, other department also there are some students who got this kind of award.
Okay.
Actually, this project is funded by Seagate for quantum dot-based fabrication. When I could look this project when the third year of this project, when I was went into, and there was some problems, and actually they couldn't solve exactly why this laser worked properly. Actually, this IV curve. The IV curve is very important for detectors people. I mean, this is my always in my doctorate I work on this kind, but they couldn't explain this structure works like that. I saw that after 2 years they understood that they forgot the process. We say annealing. When they do annealing, the device structure is getting better and result is getting better. And for example, this the annealing time. This is first when in the beginning. When you do anneal, for example, 30 seconds, your device shows better performance, and the longer annual time, at least we reach this results. And also you can see the LI graph. LI graph is very important for laser area. It shows that when you go to further annealing, the threshold current is getting better. And this graph also shows the crystal quality. It means the kind of resistance of the device. We say shunt resistance. Shunt resistance shows the quality of crystal, and also it means that when it is the annealing time, the device shows better crystal quality. It means our crystal quality is the most critical things in our field. Yes.
What is quantum dot laser?
Oh, quantum dot. Okay, quantum dot. You know, around quantum dot is around, for example, 5 nanometer or 10 nanometer size atomic cluster.
Is it quantum mechanics?
Yes. When you measuring the size of
Entanglement.
not exact entanglement, entanglement part is very further.
Yeah.
I believe that entanglement may be worthy, but for laser bulletproof and paperless. But quantum dot, you can do many, you can do anything that material will shrink the size of the material. When you shrink the size of the material, the device bracket you can change. And here, when we grow the crystal, we use different crystal lattice constants, and this, for example, this factor goes layer by layer. Then you grow the crystal. If you want to produce quantum dot, you need to use different crystal constant. Normally, in detector, you don't want to use different crystal constant. But if you want to produce quantum dot, you need to use different crystal constant, and this crystal different because of the different crystal constant, this part behave like a grow a kind of small atomic clusters, and you can manage the size of this cluster. You can manage the wavelength of this laser.
Yeah, when you mentioned about quantum, then photon polarization.
Yeah.
For particle speed, is the 80.
No, here not yet, but quantum also single photon emitters also can be based on quantum dot devices. But here, just quantum dots, using quantum dot, for example, this kind of laser has some advantages. For example, when you change the temperature, the threshold of the laser doesn't change much, but normal quantum laser, the alternative of this laser is a quantum laser. It's just quantum is the size of, because of the size of the material layer, very small, and you couldn't look at kind of bulk materials. Because of this, when you change the size, this material behave a kind of mechanical structure, quantum mechanical structure. Actually, after this project, the Ohio, I passed in Texas.
Is this quantum dot technology recommended for high power lasers?
Actually, I searched on internet about high power laser. Mostly they use quantum based device. I didn't see any high powered quantum dot laser. They use broad area laser mostly. For example, they use very stack, and they can reach, for example, 5 kilowatt laser like that. But I didn't see any kind of this. Why they use quantum dot material system? Because of CK was planning to use this laser for the rider. You know, and they this kind of laser produce very sharp spectrum, and also the wavelength cannot change too much with the temperature. Also, threshold doesn't change much with temperature. They chose this kind of.
Do they still require cooling?
This wavelength, no. This wavelength is 1.55 micrometer. It is kind of shortwave infrared, but they here they don't need to cool down. Yes, thank you. But for this study, actually, we are yes. After this project was started also as a postdoc researcher in the university. Also, this is a kind of semiconductor laser project. But here the wavelength is different than Ohio State project. This wavelength is 3 micrometers in the emission wavelength, laser emission wavelength, 2 micrometers. And we need to cool down the system using this system. And we around 70 Kelvin. And otherwise, laser doesn't work. And in this material system, we say actually here the project about ICL. ICL means interband cascade laser. Interband cascade, for example, if you want to see mid-wave, if you want to emit mid-wave wavelength, this structure is most useful for 2 micrometer emission. But there are some problems. And for example, here our device has some problems. Normally, this slide means this graph. In this graph, actually in Ohio, our laser is electrical injected laser. In this project, our device is optical pump injected laser. We were injecting the NDF laser, infrared laser, for emission, for the emission. Here you see there are some, this is NDF laser, and here there are some nonlinear optic system. It emits UV light, UV laser, and using this device, we change the wavelength of the NDR laser, and using also this device, we can switch the wavelength of the infrared laser. And actually, I booked this setup when I first came. Everything was shut down, and it took almost 4 months. And yeah, I was very successful because at least we saw the signal very properly. My professor said, actually, after this, they did the same study, and they couldn't see the signal actually immediately, and it took maybe 1 week. And here, we put the device in here, laser. We emit shine, and we pump the laser this side, and laser emit this side. The semiconductor laser emit this side. And this pump wavelength, pump intensity, power intensity, is emitted wavelength. Here there was a problem. Actually, they saw a lot of they saw some problem. This graph they did it many times, but my professor said there should be a problem because when you increase the temperature 80 Kelvin to 100, the slope somewhat getting better. Normally, when you increase the temperature, slope should be worse, and I mean decrease, and somewhat increase. Actually, they couldn't understand what is going on in this system. I did a lot of measurement, then I did some literature research. I understood that the thermal conductivity of these material systems behaves very differently. Normally, thermal conductivity, when you increase the temperature, thermal conductivity should decrease. But around 140 Kelvin, thermal conductivity increase, then decrease. Actually, Now we are working on this measurement. We will now on process of writing a paper. I hope after until this year we will publish a paper about this study. Okay, this is my last slide.
This is the basic generation.
Yeah, actually, yes. Thank you so much. This question is very important. Maybe I forgot to some explain things because the backgrounds are very different. This, yes, we apply the pumping our semiconductor laser. For example, you see, we are pumping laser device, semiconductor laser device, and this semiconductor laser emit laser. This, yes, we say optical injected laser. Why they are using this material? This material is very important for also atmosphere transfer.
Why do we have 90 degree? Because vertically and
Excuse me.
you pump
Yes.
vertically and then
Yes. Yes. Yes.
is that in splitter or
Actually, this is the optical setup. The laser, this laser here, and it comes here and reflected. There are some mechanical.
number 17? It's splitter, yeah? In splitter or
70?
yeah.
Okay, yes, here. Yes, for this the detector. Actually, we want to see how much power applied on the laser. We want to see partially of the power of the laser. And we split the laser partially. We saw how much split, and we know, and we can calculate the power of the how much power we apply on the semiconductor laser. Sorry, actually, this is like that. This is semiconductor laser, like that, things like that. This surface of the wafer. Our pump beam comes like that,
Yeah.
and this device shines this way. But
Is there a reason that we choose it really big?
because normally they optical pump they work. Actually, there's the reason why because this part, the crystal edges, works a kind of mirror, and mirror reflect, and this side a kind of cavity. And we don't use any extra mirror for semiconductor. Mirrors work, and our pumped laser not goes. Okay, and I use okay. We don't apply circle. We apply kind of this shape, and it goes, and this size works as a laser cavity. And it emits this side because this part is works as a
It reflects.
as a mirror.
What is the source size?
Source
Size of the laser.
this size.
Diameter.
Okay. This diameter is around now 200 micrometer. 200 micrometer, yes. We try to shrink it. Actually, I try to shrink 200 micrometer around, yes, maximum 200 micrometer. But also, here there are some spherical lenses for to change the shape of the beam.
My question is to understand the mechanism.
Oh,
Actually, right?
No.
So, for example, you know that the laser is directed energy. So
Yes.
it may be focused.
Yes.
collimation?
Actually, we don't want to collimate. Actually, here we use some telescopic lenses for carrying the light. After the telescopic, first we open the laser beam, then carry,
Yeah.
then shrink it, and after collimation, we use spherical lenses. Here, maybe two cylindrical lenses, sorry. Two cylindrical lenses that shrink the laser dimension, the scope dimension, and they apply on the device.
Is that for precision?
Sorry?
The shrink is for precision, right?
Yes, it should we use a lot of adjustment. This the thickness is very important for the foundry. During the shrink, there is a limitation.
Thank you very much for the presentation. Sorun.
Ekranlar çok sağlam. Beyler, bütün zararları var. Onun için de bu sistemi kullanmışlar. Yani birkaç